Hello everyone, myself Kunal Bhargav. In this video, I am going to solve first test paper of analysis and design of algorithm. So in this PPT, we have the questions of the internal test papers and solution of that question paper. First question. Complete the table 1.0 after simplification of corresponding recurrence relation. In this table, we have the algorithms like linear search, binary search, factorial, tower of Hanoi, binary tree traversal, merge sort, quick sort, extractions, matrix multiplication, Karatsuba integer multiplication, and their relations. Now we have to find time complexity, space complexity, and power complexity of that algorithm. Now we will see the complexities. There are three types of complexities: time complexity, space complexity, and power complexity. Now time complexity. Time complexity may depend on various factors such as the specific inputs to the algorithm, the efficiency of the implementations, and the use of any auxiliary data structures or algorithms. In practice, the actual running time of an algorithm may also be affected by various external factors such as hardware limitations, operating system overhead, and the size of the input data. Now, space complexity. Space complexity may also depend on other factors such as the implementation details and the specific inputs to the algorithm. In some cases, the space complexities may also be affected by the use of auxiliary data structures or temporary variables. Now, power complexity. The power complexity of an algorithm is a measure of how the algorithm running time grows as the input size increases. It is typically expressed in terms of the exponent in the running times big O notations. Now note that the power complexity of the algorithms are not the same as their time or space complexity. The time and the space complexities may have different constraints or lower order terms that affect the actual running time or memory usage of the algorithm. Now we will find the time complexity of the linear search. The recurrence relation for the linear search algorithm is Tn equals to Tn minus 1 plus OC, where n is the size of the input and C is the constant time taken to compare an element in the list with the target element. To solve this recurrence relation, we can use the recursive tree method. The recursive tree relation can be written as Tn equals to Tn minus 1 plus C to n minus t time, n minus 1 times. So we'll find out the time complexity of linear search, that is 0 in bracket n. Therefore, the time complexity of the linear search algorithm is 0 in bracket n. This is because in the worst case, the algorithm needs to compare every element in the list with the target element. Now, space complexity of linear search. The space complexity of the linear search algorithm is 0 in bracket 1 because it does not require any additional space beyond the input list and a few constant variables used for indexing and comparison. Now the power complexity of linear search. The power complexity of linear search is 0 in bracket n, which means that the running time of the algorithm grows linearly with the size of the input data. In other words, if the input data is double, the running time of the algorithm will also double. The power complexity is expressed as the component in the big O notation, which represents an upper bound on the growth rate of the running time as the function of the input size. The power complexity of linear search is relatively simple and easy to understand, but it may not be most efficient algorithm for large datasets or complex search conditions. Now we will see the time complexity of Tower of Hanoi. The recursive relation is Tn equals to 2t in bracket n minus 1 plus OC, where n is the number of disks to be moved and C is the constant time taken to perform a disk move. To solve this recurrence relation, we can use the recursive tree method. The recursive relation can be written as Tn equals to 2t n minus 1 plus C and so on. So for this recursive relation, we will find out the time complexity of Tower of Hanoi, that is 0 in bracket 2 to the power n. Therefore, the time complexity of the Tower of Hanoi problem is to 0 in bracket 2 to the power n. This is because in the worst case, the algorithm needs to make 2 to the power n minus 1 disk moves to complete the problem. Now, space complexity of Tower of Hanoi. The space complexity of the Tower of Hanoi problem is 0 in bracket 1 n because of function calls itself recursively n times, and each call creates a new stack frame on the call and stack. The call stack therefore has a maximum depth of n, which is the space required by the function. Now, power complexity of Tower of Hanoi. The power complexity of the tower of Hanoi algorithm is 0 in bracket 2 to the power n, which means that the running time of the algorithm grows exponentially with the size of the input data. In this case, the input data is the number of disks that needs to be moved from the source page to the destination page, and the algorithm works by recursively moving smaller disks from the source page to a temporary page, and then moving larger disk from the source page to the destination page, and finally moving the smaller disk from the temporary page to the destination page. The total number of moves required to solve the problem for n disks is 2 to the power n minus 1, which gives the algorithm a power complexity of 0 in bracket 2 to the power n. Note that the Tower of Hanoi algorithm is a classic example of a recursive algorithm with an exponential time complexity, and it is often used to teach the principles of recursion and algorithm analysis. However, for large values of n, the algorithm can become computationally expensive and impractical to use. Here are the time complexities for the table which has given the algorithm's name like linear search, binary search, factorial, and so on. The time complexity of linear search is 0 in bracket n, binary search 0 in bracket log n, factorial 0 bracket n, tower of Hanoi 0 bracket to the power n, and so on. Now the space complexity of the that algorithms like linear search equals to 0 in bracket 1, binary search equals to 0 in bracket 1, factorial is 0 in bracket 1, tower of Hanoi is 0 in bracket n, and so on. Now the power complexities of that algorithms: linear search is equals to 0 in bracket n, binary search is equals to 0 in bracket log n, factorial 0 and in bracket n, and so on. Now the second question: write recursive algorithm for polynomial representation. This algorithm defines a classic polynomial with a constructor that takes a list of coefficients. The evaluate method evaluates the polynomial for a given value of x. The base case of the recursion is when the polynomial has degree 0, that is, it is a constant polynomial. In this case, the method simply returns a single coefficient. In the recursive case, the method creates a new polynomial p of degree n minus 1 by removing the highest degree coefficient from the list of coefficients. If it then recursively evaluates p for the given value of x and multiplies the result by x. Finally, it adds the highest degree coefficient to obtain the value of the polynomial for the given value of x. The algorithm works by breaking down the problem of where evaluating a polynomial of degree n into the problem of evaluating a polynomial of degree n minus 1. It uses the fact that a polynomial of degree n can be expressed as px equals to x into qx plus c, where qx is the polynomial of degree n minus 1 and c is the higher degree coefficient. This allows the evaluation to be performed recursively by computing qx and multiplying by x and then adding the highest degree coefficient. There Then this is the algorithm here in which we can find the recursive polynomial representation. Now third question. Write iterative version of Tower of Hanoi problem. This implementation uses a stack to keep track of the recursive calls that would be made in the recursive version. The stack starts with the initial call to move n disks from the from road to the to road using the aux road as an intermediary. In each iteration of the loop, the top call is popped from the stack and executed if there is only one disk to move. It is moved and the loop continues, otherwise two recursive calls are pushed onto the stack. One to move n-1 disk from road to aux road using two rod as intermediary, and another to move n-1 disk from aux road to two road using from road as intermediary. Finally, the call to move the remaining disk from road to road is also pushed onto the stack. This process continues until the stack is empty, at which point all the necessary moves have been made to solve the Tower of Hanoi problem. Solution of Tower of Hanoi. This is the algorithm in which we will define the Tower of Hanoi, and we will define right there from road two road and create a stack and push the initial values. Now we will apply loop until the stack is empty. If there is only one disk to move, move it and continue. And otherwise push the two recursive calls onto the stack. And here's the algorithm in which we can find the tower of Hanoi solutions. Thank you.